You are driving at 80 kilometers per hour. You round a blind highway curve, and suddenly, a stalled truck completely blocks your lane. You slam the brakes and abruptly swerve, just barely missing it. That moment of panic comes down to a strict engineering metric: sight distance. It is the actual length of the road surface visible to a driver at any given moment. When drivers outdrive their line of sight, collisions occur. Because human reaction time is biologically constrained, designing highways with adequate forward visibility is the single most critical parameter in geometric road design to prevent crashes. To build these safe roads, engineers must arrive and apply 3 specific visual thresholds: stopping sight distance, overtaking sight distance, and intermediate sight distance. These invisible geometric boundaries define the physical limits of the road, creating a buffer designed to account for the predictable physics of a vehicle in motion. Stopping sight distance, or SSD, is the absolute minimum distance a vehicle needs to come to a complete halt before striking a stationary object. The physical act of stopping involves 2 distinct kinematic phases. The first is reaction distance. While the driver's brain is processing the obstacle and moving their foot to the brake pedal, the car continues traveling at its initial velocity. We calculate this distance simply as velocity, v, multiplied by the reaction time, t. The second phase is braking distance. Once the pedal is pressed, mechanical friction takes over to bring the vehicle's mass to a halt. This deceleration distance is calculated as velocity squared divided by 2 times gravity times the coefficient of friction. Looking at the completed equation, we can see exactly what controls a safe stop. V is the vehicle's speed, T is the driver's reaction time, G is the gravitational constant, and F is the coefficient of longitudinal friction between the tires and the pavement. By mathematically separating the human cognitive delay from the mechanical physics of braking, engineers can establish exact, reliable safety margins for any posted speed limit. That baseline equation works perfectly for a flat surface, but real-world highways must constantly navigate hills and valleys. When a car travels down a slope, gravitational acceleration counteracts the tire friction. This physical pull makes stopping much harder, and the required braking distance stretches out significantly compared to a flat road. To adjust for this in the SSD equation, we modify the friction variable in the denominator. We subtract the slope percentage, or n, for a downhill grade, which reduces the overall friction value. For an uphill grade, we add n because gravity actively helps slow the car down. The topography directly dictates the required safety buffer. A driver descending a mountain pass naturally requires far more geometric visibility to stop than a driver on flat terrain. Stopping is a single vehicle action, but passing a slow-moving truck on a 2-lane highway is a complex multi-vehicle interaction, making it the most dangerous maneuver on the road. We measure this with overtaking sight distance, or OSD. OSD is broken into 3 physical stages. Stage 1 is preparation. The fast vehicle trails the slow vehicle while the driver assesses the oncoming lane and decides to pass. We measure the distance traveled during this reaction phase as D1. Stage 2 is the maneuver itself. The fast vehicle sweeps into the oncoming lane, accelerates to overtake the slow vehicle, and safely merges back into its original lane. This entire distance is measured as D2. Finally, Stage 3 introduces an opposing vehicle, Vehicle C. There must be a guaranteed safety margin, distance D3, between the point where the passing vehicle returns to its lane and the position of the oncoming car. Because engineers must calculate the high-speed kinematics of 3 separate vehicles interacting at once, the total required overtaking sight distance is drastically longer than stopping sight distance. In mountainous or highly developed areas, providing full overtaking sight distance is often impossible. In these restricted zones, engineers rely on a fallback standard, intermediate sight distance, or ISD. The formula is straightforward. ISD equals 2 times the stopping sight distance. This provides exactly enough visibility for 2 opposing vehicles to spot each other and brake safely if they meet in a restricted passing zone. Daytime visibility is only half the equation. Environmental conditions change the geometry, specifically at night on vertical sag curves, where the road plunges into a valley and climbs back out. Here, total darkness means a driver's visibility is strictly limited to the physical reach of their headlights. This introduces headlight sight distance, or HSD. Because a vehicle's headlamps have a fixed upward cutoff angle, the beams will eventually strike the rising slope of the valley ahead. Engineers must flatten the curve of the road itself so the headlight beam can reach far enough to provide safe stopping distance. Geometric design isn't just reacting to daytime topography, it requires moving tons of earth to physically accommodate the limitations of automotive lighting. These visibility rules also apply to junctions through intersection sight distance. Approaching cross-traffic requires clear lines of sight, meaning engineers must map out and enforce strict sight triangles across the corners of the junction, completely free from buildings or tall vegetation. But this raises a major practical problem. How do you solve these kinematic equations when every driver has a different reaction time and every vehicle has a different seating height and braking capability? To ensure network consistency, organizations like the Indian Roads Congress mandate empirical baselines. As this table of IRC standards shows, they dictate universal inputs: a driver eye height of 1.2 meters, an object height of 0.15 meters, and a standard reaction time of 2.5 seconds. Highway design is a careful balance. It merges theoretical physics with rigid, legally mandated empirical baselines to ensure a universal standard of public safety across the entire road network. This comparative matrix outlines how engineers deploy these distances based on the situation. Stopping sight distance is used everywhere to prevent collisions. Overtaking distance enables two-lane passing. Intermediate distance acts as a two-way fallback, and headlight distance guides nighttime sag curves. For exams, you can easily recall the underlying kinematics through two simple sequences. For SSD, the sequence is see the object, react, brake, and stop. For the more complex OSD, the sequence is see the gap, accelerate, pass the vehicle, and return. When calculating these values in a university or GATE exam, watch out for standard traps. The most common errors are failing to convert velocity from kilometers per hour to meters per second, entirely omitting the reaction distance from the final sum, and forgetting to adjust the friction coefficient for downhill gradients. Accuracy in these derivations is essential for professional exams, and in practice, prevents the miscalculations that lead to catastrophic failures in the field. These invisible sightlines are what ultimately dictate the real-world placement of retaining walls, bridge abutments, and tunnel approaches. Let's test your conceptual understanding before you go. First, based on the physics we covered, why exactly does the stopping sight distance mathematically increase on downhill gradients? Second, mechanically speaking, why does overtaking sight distance require vastly more track length than stopping sight distance? Post your answers and your formula derivations in the comments below. True engineering mastery comes from understanding the physics behind the code.